Hi, how's it going? I know it's been a while. It's been a hot minute since I last posted, almost a week, which in my timeline is a long time. A few things have been happening. First of all, I've just been in a rut lately. Like, there were a bunch of videos that I wanted to, a bunch of tutorials that I wanted to make, and I'd go and develop them, but then, like, there'd be bugs, and it's annoying. It's annoying. It's frustrating, and it sort of slowed me down a bit. As well as that, I've got a secret project that I'm working on in the background, which I can't say too much about it at the moment. But I've also been redoing all of my old code. So if you look at my GitHub, at the moment I'm doing the PyOpenGL stuff. I'm updating all of that. But yeah, anyway, onto the main topic today, which is data-oriented design, creating and deleting things. Now, I did record a previous version of this, but the code was buggy and the video was rambly, so I'm going to try to keep it as, well, within reason, without skimping on explanations. I'm going to try to keep it concise. Okay, so to start with, I'll just have a look at a refactor that I did, because I was getting to the point where I had a class which managed all of the data in the scene, and I made these helper functions, but then I found that I was passing a lot of NumPy arrays and returning a lot of NumPy arrays, and the function prototypes were just getting monolithic. And I wanted to get away from that. So what I did is I more or less created a whole list of lists as global memory, and I'm working with that. So if you imagine, I'm going to call this a table. And this table is a list of NumPy arrays. So we have one array and another array, and so on and so on. And if you check out the data schema here, we can see, for instance, okay, let's say I want to get information about my instances. So I want to know, for a given ID, an integer, what instance type is that? And this data schema is saying, okay, well, if we look in the set of arrays, this will be the ID, and this will be the instance type. But then we'll go on and on. And so let's look at positions, for instance. So each of these things are completely independent tables. So if we were to, this makes sense. Okay, here's my notes from previous video. So if we were to compare, then we would see, write this out as a table. These IDs are not implicit, by the way. That was one of the sources of bugs. But imagine we have just a simple table with like an ID number and a type, and the ID is the primary key of the table. But then if we were to look at position, our primary key, again, would be the ID, and then the position would be the associated vector 3. And that is sort of how everything is working. So if we look back at the full schema, everything has an ID, that's the primary key, and that is used for everything. So if I go and update a position, we look through all the IDs, we see the ID, we look in the cube transforms or the light transforms or something, match up the appropriate ID, and then set the matrix data for that matching ID. And I'll talk about why that's important in a second. But on to the topic, which is creating and deleting things. So let's say that I want to create a bunch of, I don't know, it doesn't matter, does it? A bunch of things. Let's start with a list and throw in a bunch of numbers. So we say, okay, here's number 0. We created a thing, we put it on the list. But see that, well, right now, we have a size of 0. So when we throw something on, we'll have to increase the size to 1, and we'll do what's called a realloc operation, where we allocate a new chunk of memory, which has the appropriate size that we want for the final result. We copy any existing memory into the allocation, and then set that allocation as basically the pointer or the thing, which is the data location, the final thing. Okay, so this is a little silly example, but let's say we want to create ID 1. We look at that and we say, okay, we're creating ID 1. It's going to go in at position 1. We have a size of 1, so we're going to have to realloc Now we'll go, okay, we'll allocate something of size 2. We'll copy over the existing data, and then we'll set that as the new location or the new thing that we're working with, overwriting the original, and then we put in the new entry. So far, so good. Now, there are a number of variables which we'll need. So if we look at this, we are interested in, like we'll say, we have this allocation, this list, and it's filled up to position, like it's filled up with 2 things and has a maximum size of 2. And it turns out, I'm really trying to keep this concise. It turns out the optimum strategy is doubling the size of the array every time we add something in. Mathematically, that's the best way to do it. Now, why is that? Well, let's say we just increase the size by 1. That's a naive strategy, works pretty well. But let's say we do n things. We have a resize of 1 element, a resize of 2 elements after that, and then a resize of 3 elements. All the way up to we need to resize the final size of n, because every time we throw something in, everything gets resized. Okay, now, if you're familiar with basic math, we take the first and the last as pairs. So this is, n plus 1, and then these ones, again, sum up to n plus 1, and so on. So we have n plus 1 is a sum per pair, and then there are n numbers here, so n over 2 pairs. This comes out to order n squared, but that's order n squared to add n elements, and so if you average that out, you amortize that out, on average, it's a linear operation every time you add something. That makes sense? Okay, well, let's say instead of that, we're doubling every time. So we have 1, 2, 4, and I'll write this. Because how many times are we going to double? We're going to double log to the base 2 times. Because think of it as we have a problem. The problem is we want to add n things to the array, but then we're halving the size of the problem every time. I think that makes sense. All right, so if we look at this, this is an geometric series. It's a geometric series with an initial term of 1, a ratio of 2, because we're doubling every time, and let's say how many terms we adding? Log 2n. And so the sum is given by, if I remember this correctly, it's, I want to say this. Okay, I think that's correct. Right, so a equals 1, doesn't matter, it's 1 times some stuff, and then here we have 1 minus, and then of course this is 2 here, and so 2 to the log 2 cancels out, so we have 1 minus n over negative 1. That's n minus 1. So that is order n, a linear operation to resize n times, and so amortized out over n operations, that's an average constant resize time. In other words, on average, we can expect, if we're doubling every time, on average, we can expect that most times we add something, a resize will not be necessary. Now, is worth noting that's on average, and occasionally a resize will be exceptionally expensive because we're doubling the size, but that's the price we pay, I guess. So that's the theory. Now there's one other thing that I haven't noted, because right now I'm just adding on numbers, but these numbers actually represent things. So in our engine or our system, that they could represent, for instance, IDs of objects which have been created. And we don't just want to keep creating things. So we go 0, 1, 2, and then we delete object 1. Let's just leave deletion for now. The next thing we add, we don't just want to add 3 because we're missing numbers. And if we have a system that keeps destroying things continually, we might run out of numbers. We want to have a system that reuses things. So what I've done as well is I've created what's called calling it a garbage bin. When we delete an ID, we pop it onto another list, and then before we create the next ID, we check the garbage bin and say, is there an ID which was previously deleted that we can reuse, and then remove that from the garbage bin. Now, that gets me on to the next bit, which is deleting things. And I promise, I swear, I'm trying to keep this concise. It really does bother me when I know that I'm spending too long to explain something. Anyway, so 0, 1. Okay, this is a fair case. Let's say we want to delete object 1, instance 1. Our goal would be to have in the end something like this. Again, naively. So I guess, what's the most naive way of doing this? Maybe create a new list, copy over everything that isn't the thing we just deleted. That's not great. That's really not great. Okay, what's another thing we can do? We could take the old list and run a for loop and copy over so that we get something like this. I mean, that's a little better. And then remember that we have another variable called count. And count we can think of as like how many things are we really interested in this array. So currently count would be 5 because we have 5 objects that we're managing. We just deleted 1, so it's okay to keep that extra 4 in memory. We can just decrement the count and say count equals 4. And yeah, that's fine. This last entry would be overwritten when we go and create something new. Fine. Okay, but this has taken a number of operations to shuffle things along. And then as the size of the array gets larger and larger, that's bigger and bigger. So here's a better approach. Let me just sketch this out again. Okay, we want to delete this thing. What we can do is we can pick the last element on the array, overwrite the position that we want to delete. That's always one operation, no matter how large the array is. And then just do the same thing. So again, that position has been overwritten, whoops, with the end. The end number is still there, but if we were to decrement the count variable by 1, then it doesn't matter. It's a garbage number. Our system doesn't care about it. It's not going to see it. So that brings me on to the idea of the idea of everything having an ID associated with it. So in previous situations, I was very trusting of, we'll say that, very trusting of the transform system, that when I saw a position or an Euler record, I could sort of read that ID implicitly. And this is an edge case, which is an issue with that. So here we have 4 objects, and the first 2 are cubes, so they have Eulers, and the second 2 are positions, so they have light data associated with them. Now let's say we want to delete, what am I thinking? No, I got that wrong. Okay, the first 2 are lights, there we go, and the last 2 are cubes. Okay, let's say I want to delete light number 2. So I look on here and I say, okay, there's light number 2. Swap that with the end. So see here we have the start. That's been swapped out. And thing 3 is still in position. Now, if we were reading this in order, so like the first time I see an Euler, that corresponds with the first position that I saw. Then, yep, Euler 1 is corresponding to cube 3, and Euler 2 is corresponding to cube, with the ID of 4. But in this case, because I'm still trusting that things are ordered correctly, then Euler 1 would be associated with the other cube. In other words, the cubes have swapped angles, swapped rotations. And that is a peril that comes with trusting the system too much, and it's a nightmare to debug, and it's just a thing to be aware of. Yeah. So anyway, and there's another thing which was really useful, and that was the concept of sort of an object type. So here I'm using object type 0 to represent a cube and object type 1 to represent a, what am I thinking? A light. And then each of these will have a sort of component associated with it. So for instance, we can see a cube has a position and a rotation, but no light data, and a light has a position, no rotation, and some light data. And this can actually be encoded in simple numbers. So if we were to give position a value of 1, Euler's a value of 2, and light a value of 4, then that would actually correspond to setting the following bits. So we set nothing, 1, 1, and then for object type we set 1, 0, 1. This corresponds to the number 3, describing the components of the cube, and the number 5 describing the components of the light. Now that can then be extracted by bitwise operations as a simple test to check, hey, if I'm updating an object, what am I thinking? If I'm updating an object, which components does it have associated with it? And then go and update those as well. But anyway, that's enough for now on the paper. Let's have a look at the code. So here we are now looking at the code, and I've put a lot of work into refactoring this to actually remove the class from the model. And yeah, so if we were to look over at the app is now no longer dealing with a scene class. It's pretty much just dealing with the model module by itself. So if we were to go and update things, we just call update on the model module. It was reaching a point where I figured it was starting to get over engineered. It probably is way over engineered already. But yeah, so here we have the components description and all of the data for the tables. And this is really not that well described in this code. Ideally, you would sketch the schema, the data schema out by hand and refer to that, like a good documentation, for instance. But I'm rambling. Let me just get in and do a little demo. And this could be completely buggy. Like, I've spent a lot of time finding bugs and removing bugs. There are probably still bugs. That's fine. I've accepted that. Okay, so here we are. I'll just hit keypad 1 to add a cube. Maybe it didn't. It adds at a random position, so I'll just zoom back a little. There we go. There's our cube. Let's create another cube. That's great. And now keypad 2 to delete cubes. So we'll delete one at random. There we go. And another one. And another. They're all gone. If I keep pressing delete, nothing happens. Okay, so let's add a bunch more cubes and let's add some lights. So keypad 4 to add a light. Where was that? There we go. Okay, let's add some more. There we go, got a whole bunch of lights. I'm using a storage buffer for the lights so it can handle an arbitrary amount of lights. Now you will note that the frame rate is tanking. Well, what is it, you say? Wasn't it previously doing like 4,000 frames per second? Yes, it was when it was compiled. Now, Number is pretty good, but everything that I've done at this point to try to improve the readability of the code, NumPy just hasn't been feature-rich enough to handle it. It's possible that I cause myself more mental torture and refactor it and get it compiled. It's also possible that I just go to C++, honestly. The hassle I've had with this. Okay, anyway, we can also delete lights. So keypad 5, delete a few lights, delete some cubes as well. And as far as I can see, there's no obvious bugs at this point. I think. Fingers crossed. There we go. Okay, everything's deleted. So that's it. That's creating and deleting things, data-oriented code. I really hope you enjoyed this. This took me a lot of pain and debugging things by hand on paper, which is not fun. And I hope that this code doesn't produce too much anguish, but just know that I did my best on this one. Okay. let me just quickly go through this. Okay, so just the positions, for instance, to show the base algorithm. So if we want to add a position entry, okay, no problem. We'll just identify the target arrays that we want to, use to represent the IDs of the position and the position data. Okay, we've got all of that, size and count. And we check the size. If the size is too small, we'll reallocate, basically doubling the size or adding one, depending. Copy everything over from the original array. This needs to be written back into the original tables, but we'll also keep a copy of it for semantic, like something nice that we can refer to. Then we simply add the ID at the end of the array currently, and then add in the positions at the end of the array, and then increment the count variable by 1. Okay, so double if necessary, add on to the end, that's creating things. Now, as for deleting things, it pretty much goes like I was saying. So again, extract the arrays that we're going to work with from that large set. And then, where are we? Try to identify the index that matches the ID that we're looking at. So like we're saying, hey, delete instance number 7, but that instance number 7 may not be in the 8th position. It may not be in order. It might be all randomized. So we need to search through and find the position corresponding to the ID of 7. And then wherever that ID was, basically swap it with the end element. And same thing here, swap it with the end element, but just swap a whole chunk of data corresponding to the XYZ. And then decrement the appropriate table count. And that's it. Okay, yeah. As I keep saying, I really hope you enjoyed this, and yeah, stay groovy, keep coding, have a good one, and I'll see you around. Bye.